Hi everyone, in this lesson we're going to go through how to handle transformations for a radical parent function. So similar to a quadratic, a radical is a type of graph that we use. A quadratic uses x squared, whereas a radical uses the square root of x. So a lot of the conversation from the previous video about quadratic functions is going to carry over with radicals. It's just that now we're going to handle it in terms of square root values. So everything here is kind of the same. They still have a center coordinate called the vertex. There is no axis of symmetry on this because it's not symmetric. It's sort of like half of a quadratic just turned on its side. But the domain and range is actually pretty much the same. So I have shift here depending on whether the graph shifts up or down or left or right. So the domain is impacted whether it's shifted left or right, whereas the range is whether it's up or down. So they basically go to the right forever. It's really hard to see in my sort of parent function graph here, but if I was to continue reading the graph going to the right, it's going to keep going on forever. It's going to keep increasing, it's going to keep going up, it's going to keep going to the right forever, but it doesn't really do a lot in this area. And the reason for that is because when we do the square root of, let's say, 4, we know a number times itself, that's 4 is 2, but if I try to do the same thing with a negative, well, if I do 2 times 2, I get positive 4, and if I do negative 2 times negative 2, I get also positive 4. So there is no real number that works, and if you might remember this, we're going to come back to it, but the number is what we call complex. So this would actually be 2i. If you remember imaginary numbers from when you took algebra, maybe in a previous course or earlier in your educational career, if I multiply 2i times 2i, I get 4, and then I squared. Well, I squared is the same thing as multiplying by negative 1. So we can't actually do the square root of a negative because it's not a real number to graph. So that's how we end up with this shape. So let's talk about the transformations. I've got good news in that all the transformations we previously studied kind of just carry right over. So this is kind of the nice thing, is that my transformation here is the square root of x minus c. So if it's a minus c, the graph will actually move to the right, even though it's in the positive direction. And if you're adding, it actually moves it to the left. So for example, you can see that the vertex here is at the coordinate point 3, 0. So my graph essentially moved 3 to the right. So the equation would be x minus 3. The reason it does the opposite is let's plug in this x coordinate and see what happens. So if I plug in 3 into 3 minus 3, I get the square root of 0, which is 0. And so that makes sense for my y coordinate. So what we have to do is we have to counteract what's happening to x, which is why it's always the opposite. Now, if the graph has a plus or minus on the outside, it does exactly what we think. So a plus c will move the graph up, and a minus c will move the graph down. So we can see here that the vertex of this graph is 0, negative 4. So the graph actually moved down by 4. So what we would say is the square root of x minus 4. And so again, let's plug in this x coordinate and make sure this makes sense. So when I plug in 0, I get the square root of 0, which is 0, minus 4. And so that makes sense as my corresponding y coordinate. So our graphs basically follow these transformations. And the way I like to describe it is this is inside of the structure of the graph, so it changes the structure, which is why we have to change the direction. Whereas this one is just kind of added on top, which is why it moves it up or down, because we just kind of throw it on top of the value. So it's interesting in that when we apply the transformations in this order, we actually kind of do this sort of opposite on the inside, same on the outside rule. Some other notable transformations. So we talked about shifting it over the x-axis. So if it's negative in front, this will flip over the x-axis. So you can see right here, this is the negative square root of x graph. My vertex is still 0, 0. Now, what we didn't have before is the negative inside. And you may remember from a previous slide, I just said that you can't have a negative. Well, you can't plug in numbers and know the value at a negative. But what happens here is this will actually flip the graph on the y-axis. So you can see here, this would be the normal shape graph going this direction, but it goes the other way. So that gives us numbers like -4 and -9. And you might be wondering, why does that work? So let's make a little chart here and show you why that works. So if I plug in -4 into this equation, the square root of -4, well, two negatives make a positive, and that's how this actually works. So when we plug in the double negatives, they actually counteract each other and produce a number that we know, 4,2 and 9,3, which you can kind of see on the graph. So outside flips it over the x-axis, inside flips it over the y-axis. This does not exist in a quadratic. And the reason why we didn't talk about it is because if we did this to a quadratic function, I have -x squared. Well, that's just x squared. So if you remember, we talked about the axis of symmetry. Well, that's basically my y-axis. So if I flip the graph over the y-axis, I end up with the same exact shape. So nothing actually changes. So this is why it didn't really work in x squared graphs. And then again, we still have stretches and shrink. Now, I don't want you to, be too focused on this. What I just really want you to know is that if the C is on the inside, this is what we call a horizontal compression or shrink or stretch, okay? If C is greater than 1, it's going to shrink the graph horizontally, which means it's going to move the graph sort of like inward. And if it's horizontally stretched by something greater than 1, in between 0 and 1, it's going to move the graph kind of out more. So this is a stretch because the graph is kind of like going out further, essentially. And then this is the one that's a little bit more important, the vertical stretch or shrink. If C is greater than 1, it's going to move the graph essentially like it's going to make it go up more. And if it's in between 0 and 1, it's going to compress it down. So you can see right here, this graph is like compressed downward. So this would be a vertical shrink. These are tough to establish, but just in general, what we want to understand is that when we multiply, it actually impacts the x and the y coordinates. And so that's really the main idea here. What's really easy with this is it just multiplies all the y coordinates by c, whatever that number is in front. So if C was 5, you'd multiply all your y coordinates by 5. If C is 2, you multiply everything by 2. This does the opposite. So it would either multiply by the reciprocal. So for example, if I had the square root of 2x, what this will do is it's going to multiply all x coordinates, not by 2, but by its reciprocal of 1/2. So that conversation about inside does the opposite, outside does the same still holds. So in general, let's focus on just understanding all the shifts, and then we'll talk about increasing and decreasing in this chapter as well. So my function here, now again, our normal vertex is 0, 0. This graph has been shifted. So again, inside is opposite of what it's doing. So it's a -4, so it's actually going to shift it 4 to the right. And +6 moves it 6 up. So if I take this coordinate point, 0, 0, move it 4 over and 6 up, I'm right there. So that's actually going to be my new vertex. So let me get rid of this part here. Okay. And so my graph is positive on the outside, positive on the inside. So it's going to go in a pretty normal direction this way. But let's say you're not 100% sure. Here's a quick way to do it. It's not the best, but let's start with my vertex center. Let's get a point below 4 and above 4. So let's go 3 and 5. So if I plug these two coordinate points into the equation, it will help me graph this. So let's plug in 3, and I'm going to do it up here off to the side. So I get 3 minus 4 plus 6. 3 minus 4 is -1 plus 6. And we can actually stop right here. This is, again, a problem. I don't want a negative. So the graph cannot go that direction. So that kind of helps us see that the graph can only go one specific way. Now let's plug in 5 and see what coordinate I get. 5 minus 4 plus 6. So 5 minus 4 is the square root of 1. The square root of 1 is just 1 plus 6. Well, that's 7. So now I have the coordinate point 5, 7. And you can see right there that because the graph goes from this starting point up and over, it had to have gone that direction. So again, when I think about my domain, it's how far to the left the graph starts. In terms of the x-axis, the graph starts at 4. And it goes to the right forever, so that's 4 to infinity. My range, the lowest the graph can go, is 6. And it goes up forever. Again, I know it's kind of like misleading. I know this looks like it's really going to kind of slow down, but just trust me, if you kept zooming out, it would just keep going up. It goes very slow, but it goes. And so this would be my domain and range. If you remember very early in this lesson, I said that it was shift to infinity. Well, positive 4 and 6 should look really familiar. That's how the graph was shifted. Now, what's really nice about this is that the graphs are either increasing or decreasing. And the way that we determine whether it's increasing or decreasing is whether the graph is going up or down as we read it left to right. So let's start at the leftmost point. So that's right here at its vertex, 4, 6. If I go to the right, you can see my little cursor going up in value. So that means the graph is not decreasing, but is increasing. What throws everybody off is we want to answer this on x values alone. And what I mean by that is it's increasing on the x value 4 to infinity. So my increasing interval would be 4 to infinity. So basically, and I'm going to kind of tell you this because for these graphs specifically, whatever the domain is what the increasing or decreasing interval is going to be for a square root graph. It's just determining whether they increase or decrease. Okay, so let's try another one. So let's identify the shifts that are happening. So again, this is a minus 3 on the outside, so that's going to move the graph down by 3. There's no other shift in terms of its direction, so let's just take it 0, 0. Let's move down 3. So I get my vertex is at 0, negative 3. And then I have this negative on the outside. So this is a flip over the x-axis. So now again, let's say you're not 100% sure which way you want to go. A quick way to do this is make a little chart. We always start with our vertex in the center. So since my vertex was 0, negative 3, I'm going to start there. I'm going to point less than 0, which would be, that looks like a 2, but it's actually supposed to be a 1, and a 1. So let's plug them in. So let's do negative 1 first. So I get the negative of negative 1 minus 3. And right off the bat, this is a problem. So the graph doesn't go that way. So now let's plug in 1. Negative square root of 1 minus 3. Well, the square root of 1 is 1. Negative 1 minus 3 gets me negative 4. So this is my next coordinate point, 1, negative 4. And so the graph would go down this time. So it's kind of nice in case you're not sure which way the graph would go. If my coordinate point happened to be, let's say, down here, then my graph would do something like this instead. So my domain would start from my leftmost x spot, which would be 0 here to infinity. My range is where it gets tricky. Again, this goes from lowest point the graph can get to the highest point the graph can get to. So the graph is now going down forever. So my range is now negative infinity. But the highest y coordinate the graph can go is up here at negative 3. Now to do the increasing and decreasing, the first thing is to determine whether it is increasing or decreasing. So if I read the graph left to right, you can see that my cursor is going down as I read it left to right, which means this graph is not increasing and therefore decreasing. And if you remember, the increasing and decreasing is always based on the x values, which in this case is just the domain. So the decreasing interval would be 0 to infinity. And that's it for these graphs. The nice part is once you get the transformation down in terms of left, right, and shifting, a lot of this is going to repeat. So there's some really good things that are happening there. Okay, and so let's look here. Now this is going to be a little bit trickier because there's a minus x and a plus 6. And I'm hoping you're saying, well, it's a plus 6, so that means it actually does the opposite. It should be going to the left by 6. And that's great. Great answer. One problem. Since the x is negative, it actually is going to be slightly different. So here's an alternate way to find the vertex. If you're never sure, the one thing that you can do is take what's in here and set it equal to 0. This will also help you find the domain and range values too. So if I set this equal to 0 and I solve for x, I don't have the vertex at -6 anymore. I have the vertex is at 6. Now the graph does not have any y coordinates. So let's just go right to the chart. So this is my vertex. If I plug in 6, let's see what happens. 4 times the square root of -6 plus 6. 4 times the square root of 0. So that's 0. And that should kind of make some sense because we weren't adding or subtracting anything here. So that whole premise that the graph didn't get shifted up or down is still there. But let's plug in some extra coordinate points because now the graph is doing some weird stuff. So let's plug in 1 point below and 1 point above like I've been doing. So let's start with the point above, or 5 at least. So 4 times the square root of -5 plus 6, 4 times the square root of 1, which is just 4. So that's my next point, 5, 4. And now let's plug in 7. 4 times the square root of -7 plus 6. I get 4 times the square root of -1. And again, oh, that's not possible. So this is the first graph in which we have the function not actually going to the right side anymore, but going to the left side. And look at that big stretch in order to make that. Two things are happening. One, that 4 is what's causing this big stretch in between my starting point and my next point. And if you just notice, by happenstance, look at this slope between those 2 points. It's actually a slope of 4. Now, technically it's a negative slope, but if we're just looking at it in terms of its distancing, it's 4. So we have that coordinate point. So my domain is different because, again, domain goes from the leftmost part of the graph to the rightmost part. But the graph is going from the left-hand side. So my domain would be -infinity. And the rightmost side would be 6 in this case. The lowest y value this graph goes is 0, but it goes up to infinity. So what happened was this negative in front moved the graph, instead of it going this direction, made it go this direction. And it got shifted the opposite of what the inside was making us think about. So since there was a double negative, basically, it actually went the same way. So if you're never sure, you can always just set this inner part equal to 0, and that will tell you where your vertex is. So it's kind of like a catch-all. And so the graph is increasing or decreasing. So again, we're reading the graph left to right. So I can't start here anymore because that's actually the rightmost part. I have to start all the way up here. So clearly this graph is now going down as I go left to right. So now the graph's no longer increasing, but decreasing on its domain of -infinity to 6. So remember, this domain for these graphs are always going to be part of the increasing and decreasing interval. All right, I hope that was helpful. I'll see you in the next video. Feel free to come back and watch anything. If you have any additional questions, reach out. Thanks.